Hi everyone, my name's Laura Gwilliams. I am extremely grateful to have my dissertation work be granted this award. I can't even begin to say what a massive privilege and honour it is. And I especially want to thank Bob Glushko for sponsoring this award and making this possible for so many years. I also want to take a moment to thank my PhD advisors, with whom I share more than half of this award. So Alec Morantz and David Popple, they have really been the most incredible PhD advisors that I could ever have asked for. They've been so supportive and they're just so wickedly smart that my research has benefited 1,000,000,000% from their input. And we've also had a lot of fun as well. So Alec and David, thank you so much also for going on this journey with me. So I'm really excited to share my work with you today. My research is trying to better understand how speech comprehension is achieved in the human brain. And in that work, you'll see that I'm trying to bring together insight from neuroscience, from theoretical linguistics, as well as machine learning. And the reason that I do that is to address this big, high-order question, which runs as a common thread throughout my research, which is how is it that the brain is able to map the acoustic signal of speech onto a coherent understanding of what is actually being said. Now, I'm sure I don't need to convince the audience that this is not a trivial problem that the brain has to solve, not least because the mapping from sound to meaning is arbitrary, but also because the acoustic signal itself is often corrupt with noise and ambiguity. So how is this done? Well, the idea is that the brain needs to transform the acoustic signal of speech into a hierarchy of linguistic representations in order to bridge over to eventually contact with meaning. So the question I have on the screen maybe is best answered if I split it up into 3 sub-questions. So the first is, what are the representations which form this bridge? So in other words, what should I put in place of those question marks? The second is, what are the operations? And by that I mean, what happens within each of those little boxes that transform one representation to another? And finally, in what order does all of this stuff happen? Well, okay, that makes some sense. Well, I would hope so, because I made the slides, but how are we actually going to figure out the answer to those 3 questions from brain recordings? So let me just briefly overview the kind of analytical framework that I've been working with it. So the idea is that we want to understand something about the psychological reality of language comprehension. And we want to understand how that is instantiated in the brain in terms of neural representations and operations like I just described. However, unfortunately, we actually don't have direct access to either of those 2 things. So that means that what I really need to do is come up with some language features which I think sufficiently correlate with the psychological reality of language comprehension. And on the other side, I also need to come up with some neural representations, some neural features that I think, again, sufficiently correlate with the processes and representations that I'm interested in. So the idea then is, having selected these features, is to try to map from one side to the other. So if I am modeling language features as a function of neural responses, I'll call that decoding. And if I'm going in the reverse direction, so modeling neural responses as a function of language features, we call that encoding. But in either way, we just are trying to form a linear mapping from brain to language. So I want to be very concrete about something. So when I say, what representations does the brain use? Well, what I really mean is, what language features can I put here which allow me to, which seem to be important for mapping between brain and language? And similarly, when I ask about operations, what I mean is, how do these representations seem to evolve over the time course of processing? And how might I infer the operation being applied in order to cause that evolution? So with that framework in hand, these are the questions that I'm trying to address. And what I'm going to do first is to focus on these first 2 questions by basically just presenting you some take-home messages from some of the studies that I conducted. So, for example,
At the lowest level, my work suggests that the input signal, so the acoustic signal, gets transformed into what I refer to here as probabilistic phonetic representations. So concretely, we found that the brain seems to represent phonetic features, but graded in terms relative to how much acoustic evidence there is in favor of one feature or another. And it also seemed to represent how ambiguous a speech sound was. Some of my more recent work found that these representations actually seem to be adjusted when listening to accented speech, and priors over those phonetic probabilities seem to also be adjusted depending on prior acoustic experience. So a lot of my PhD was concerned with the morphological level of processing, and I will refer you to this review paper which came out earlier this year, which not just kind of overviews the current state of affairs when it comes to the brain and morphological processing, but it also puts forward a concrete hypothesis about how morphemes are composed and what the kind of computational operations might be to allow that to happen. But to give you again some take-home messages from some individual studies, we found that phoneme sequences do indeed seem to be used to activate morphological units in speech processing, and that this happens in proportion to, again, the graded phonetic evidence in favor of one particular morphological sequence or another. And kind of focusing rather just the access to morphological units, but how those morphemes then get combined, so this would be a compositional operation, we found, again, evidence that this compositional process is governed by the morphosyntactic rules of the language. And interestingly, those same morphosyntactic rules seem to almost reverse engineer the morphological representations which get stored in memory. So those studies that I overviewed are all taking a very careful experimental approach to really just focus in on one single level of this hierarchy at a time. And by doing so, you can make a lot of headway into, again, what are the representations and operations. But I said to you that there's a third part of that problem, which is what order do these things happen? Well, in order to address that, what I really mean is what are the relative order with which these representations get generated? And for that, we need access to the full hierarchy of representations, going above the lexical level, also into the phrasal and sentential level. So what I'll do now is present in more detail a study which addresses this question. So for this, we recruited 21 native English participants. We had them come into the MEG lab at NYU Abu Dhabi, and they listened to 2 hours worth of stories in the MEG. Now, this resulted in responses to around about 16,000 words per participant. Now, importantly, I painstakingly annotated those stories for a range of hierarchical linguistic features. So here's a subset of those features, but in total there are around about 50 of them. And they start at the lowest levels, like I was describing, so phonetic features. We also include sublexical properties, like how many morphemes and syllables are contained in the word. Word class, so is it a determinate, noun, adjective, etc. Then we have some syntactic features as well. So how many branches of a tree can we create at a particular word, and how many can we close? And how deep into the tree structure does a particular word occur? And then we have what I would call kind of overly simplistic proxies of semantic processing, which are the first 10 principal components of the glove word embedding. So the aim of the game here is to take all of these features and try to decode them from the MEG responses of people listening to these stories. And to remind you, the question in this case simply is, well, in what order are we able to decode them from the MEG signal? So we had a few hypotheses of what the answer to this question may be. The first one is basically what I had in the beginning of this presentation. The idea here is that, okay, language is compositional, so processing is probably compositional as well. So from this perspective, the low-level representations will be decoded first, followed by increasingly higher order representations as they get composed from the constituent units. Another possibility follows the parallel computational approach. So this would say that actually all features can begin to be generated at the same moment in time. So there shouldn't be any systematic relationship between the timing of when a feature comes online and its position in the hierarchy. The final hypothesis, which is kind of the underdog of the hypotheses, says that, yeah, okay, there is a hierarchical relationship between timing and where in the hierarchy the feature is, but this is going to be an inverse relationship. So in this case, the higher order representations are going to come online earlier than the lower level ones. Now, the only real reason that this is the underdog is because it's been primarily put forward for visual processing, but not yet for speech and language research. Okay, so which of these three hypotheses do our data support? On the right-hand side, I'm going to show you the results of the decoding analysis. So on the x-axis, you have time in seconds relative to the moment that the word ended. And for each row that I reveal, it's going to be a different family of features. So let's start off with phonetic features. So what you see here is the result of phonetic feature decoding, and that little bar that you see on the timeline, that tells you basically the result of a temporal permutation cluster test of when we can decode the feature above chance. For phonetic feature processing here, it's just that we seem to be able to decode that information from around about 0 to 200 milliseconds. Sublexical features begin to be decodable about minus 100 milliseconds. Word class starting about minus 200, which is the same for syntactic operation. And then syntactic state and the semantic vectors start to be decoded around about half a second before the word ends. Okay, so what can we say then about the dynamics of processing? Well, it seems that the higher order features actually begin to be decodable first, and later on that the lower level features are decodable. And it's also an interesting relationship between the hierarchy and for how long information is maintained. So the higher order representations also seem to be maintained for a significantly longer period of time. So if I pull back my three hypotheses, what can we say about this? Well, the only hypothesis which predicts that the higher order features will be decodable earlier than the lower level ones is our underdog reverse hierarchy architecture. So this suggests that the proposition, which was originally put forward, as I said, for visual processing, may also have its place for speech processing as well. So there's one final analysis on this data set that I want to describe to you. So it's possible that this relationship between the onset of decoding and the hierarchy is almost incidental. Or something that we wanted to test is that, well, maybe actually information from the higher levels is being used to inform representation down at the lower levels. The information is being passed down this hierarchy. So to test whether that was the case, we focused in on the decoding of word class, and we asked, okay, do we better decode word class when we use the syntactic labels? So that means that a word like hammer, for example, would have a different word class label if it was being used as a noun as compared to a verb. Or alternatively, do we decode word class better when we use the most frequent word class that the item is used at, and that would be created from the bottom up from its phonological form. And what we find is pretty strong evidence that word class is indeed generated from the higher order structure, because the contextually sensitive labels is a significantly better predictor of neural responses. So not only do the higher order features come online earlier, but this information also seems to be passed down through the processing stages. So this is the little schematic that we had at the beginning of the talk, but these set of results suggest that actually when people are listening to continuous speech, an architecture a little bit more like this is better suited or better explains our observations. Why would it be structured like that? Well, one possibility is that first, information at the highest level, so semantic content and syntactic structure, serves to make educated guesses about upcoming information at the lower levels. And then, once sensory input of speech is received, this allows predictions to be integrated with the actual input. Okay, so I'm just going to conclude with kind of a higher order concluding point, which is that part of my goal for future research is to expand upon the computational aspect of my work to adopt engineering solutions from artificial intelligence to build a model that accounts for neural data, uses features as informed by linguistic theory, but also that can actually perform speech recognition tasks. And I think this is going to be an interesting and productive way forward in addressing some of the algorithmic questions that I put forward today. So with that, I want to thank again everyone in the audience, and I'll be very happy to take any questions that you might have. Thank you.